Thank you. The second paper, which is also the best student paper this year, is about the study of starvation or in congestion control. So Venkat is a 6-year PhD student in MIT, interested in performance evaluations, and then he's on the job market now.
Hello. The people have proposed many delay bounding congestion control algorithms. And despite the diversity of all of these mechanisms, they all share one key property that we identify. And we show that this property can provably lead to starvation. People want interactive applications. At the same time, traditional loss-based congestion control algorithms do not bound delay. And therefore, there has been a lot of work on creating delay bounding congestion control algorithms. And these use a variety of techniques. For instance, there are some that try to estimate the queuing delay to estimate congestion. Others look at the receive rate of the acknowledgements to estimate what rate they should send at, and yet others are learning-based. And all of these share one property that we define as delay convergence. So what is this? Well, by definition, a delay convergent algorithm is one that when run on an ideal link with a constant bit rate and a constant propagation delay, looks like this. So after a convergence time, it converges to a small range of delay variations. Now this looks like a perfectly natural thing to do, and it also makes sense to give the applications a consistent delay to work with. And this is why every delay bounding algorithm we are aware of has this property. But what we find is that this can lead to an arbitrarily large amount of unfairness or starvation. So starvation is caused by non-congested delay. What is that? Well, we can look at the total delay, the round-trip time experienced by a packet, as having three components. First, we have the constant propagation delay. Then we have the congestive delay, which is due to the queuing at the bottleneck. And then we have all other sources of delay variation. And because end-to-end algorithms can only measure the total delay, it is really hard to distinguish between congestive and non-congestive sources of delay variation. So what are some sources of non-congestive delay variation? Well, first we have Wi-Fi, which sends TCP acknowledgements in bursts of 10 milliseconds or more. And this is due to the frame aggregation feature, which improves efficiency. Cellular base stations have a complex service process in order to account for the variations in the link rate. NHOS find that it is more CPU efficient to send both packets, data packets, and acknowledgements in bursts. And finally, operating systems have various scheduling quirks, because of which they add some amount of non-congested delay variation. And to make all of this worse, one path can have multiple of these effects. So even if we build models that can understand and distinguish one of these effects, the fact that there can be multiple on the same path makes things difficult. Let's look at an example. This is a cellular link between Stanford and AWS California, taken from the Pantheon project. And as we can see, there is a lot of delay variation, partly because of link rate variation. So the y-axis is the delay experienced by a packet, and the x-axis is time when the flow is running BBR. Now let's zoom in to a region of time that is 1/10 the size of the RTT. We find that there's a lot of variation, and this has nothing to do with congestion, because BBR does not vary its rate at less than 1/10 of an RTT. And this is a telltale sign of aggregation, because a lot of packets came in, they got queued up at the bottleneck, and therefore the first packet experienced far more delay than the subsequent packets. Let's pan to the left. Here we see another type of non-congested delay, and it's really difficult even for us humans to figure out what's going on. And it's even harder to figure out what the congestive component of this delay is. And here we see that in cellular networks, we can have non-congestive delay up to 10 milliseconds. But it's not just limited to cell networks. If you look at a nice, smooth Ethernet network between the same two endpoints, we see this variation. Now, some of this is due to congestion. For instance, that is due to BBR's RTT probe. But if we zoom in to a 2 RTT window, we see that there is still a lot of complex delay variation. And again, it's hard to tell how much of this is due to congestion and how much of this is due to other reasons. And here the jitter is smaller. It's only 1 or 2 milliseconds, but it is still significant. So This is why non-congested delays can cause unfairness. When we have two flows sharing a common bottleneck, but say one of them is using Wi-Fi and the other is using Ethernet. Now, the buffer has just 5 milliseconds of congestive delay, that's the bottleneck. But because the two flows see different non-congestive delay, they're going to estimate the congestive component differently. And since they estimate the congestion differently, they're going to send at different rates, and therefore have unfairness. Now, a little bit of unfairness by itself is not a bad thing. We tolerate a lot of unfairness, for instance, RTT unfairness. But what we find is that just a finite amount of mistake in estimating congestion delay causes an unbounded amount of unfairness, which we call starvation. The first question to ask is, can we estimate congestive delay accurately? Well, people are obviously aware of non-congestive delay and have tried a variety of techniques. But every estimator that we are aware of has failure modes. And fundamentally, the problem is that the internet just has far too many phenomena to account for, and it's really difficult to model for all of that. I'm going to define starvation now. This is in a setting where there are two or more flows sharing a bottleneck. And we say that starvation occurs when the ratio of throughputs achieved by both of these flows is arbitrarily large. And furthermore, we are not interested in transient phenomena, because of course, when a flow starts up, it's going to have low throughput. But we are interested in cases where the throughput ratio remains arbitrarily large forever. Before I go into the proof, let's look at an example of a certain family of congestion control protocols, including Vegas, Fast, and COPA. While all these three have very different dynamics, they have the same equilibrium behavior, which is that they send at a rate that is inversely proportional to the queuing delay. To put some numbers into this, if the queuing delay is 20 milliseconds, they send at 1 megabit per second. If it's 2 milliseconds, they send at 10 megabits per second. And if it's 0.2 milliseconds, they send at 100 megabits per second. And here you can see the problem. We have a case where there is a very small difference in the queuing delay estimate that leads to a very large difference in the sending rate. And the small difference in the queuing delay estimate can easily happen for non-congestive reasons and therefore lead to starvation. Well, the natural question that comes up is, OK, maybe Vegas, Fast, and COPA have this problem, but there are other schemes too. So what about all of them? We prove that this does not work either. Our proof is that all delay convergent CCAs starve. And just as a reminder, a delay convergent CCA is one that after a certain convergence time has a very small delay variation. And the theorem we prove is that we can always construct non-congestive delay that is such that starvation occurs, and that this non-congestive delay is not too large, as in it is related to twice the delay variation. And the problem is delay variation can be pretty small for many of these protocols. In fact, for every protocol that we are aware of, the delay variation can be arbitrarily small or even zero. So we only need a very small amount of non-congestive delay variation in order to cause starvation. And before we prove this theorem, I'd like to prove this subclaim, which is that for any delay convergent CCA, we can find two very different link rates, say those that are 10x apart, such that they have very similar delays. And that's a problem because, again, it's easy. If the delays behavior is very similar, it is easy for the CCA to confuse between the two. So let's plot against the link rate, for a particular link rate, what is the range of delay oscillation? And by definition of a delay convergent CCA, we know that that range is going to be bounded within delta milliseconds. And let's do this for a link rate that's 10x larger. This graph is not to scale. And for a link rate that's 10x larger than the previous one. And if we keep doing that, the first thing to note is that since this is a delay bounding CCA, there's going to be an upper bound above which the delay will not increase. Again, all of this is in an idealized mathematical link. And then because of the pigeonhole principle, because the delay range is bounded, but the link rate range is not, we're going to find two very different link rates that have very similar delays. In fact, they're going to be within a range of delta. And because of this, we can construct the starvation case as follows. We start with an idealized case where there is, again, two flows sharing a common bottleneck. And for one of these flows, we construct non-congestive delay. We add non-congestive delay to the packets as a function of time. And the amount of delay we need to add is less than twice delta. The paper explains the math behind this. And the purpose of this construction is to make the sender 1 think that it is alone on an ideal link with link rate C1 megabits per second. And because it's a deterministic algorithm, it's going to do the same thing it did last time and send at roughly C1 megabits per second. But for the other flow, we construct a different non-congestive delay, which makes it think it's on a link rate with C2 megabits per second. And because even though they share the same bottleneck, they think they're alone on very different link rates, they're going to send at very different rates. So the first question that comes to mind is, OK, this is all fine for a theoretical construction, but is it really realistic? So let's look at the algorithm BBR, which is proposed by Google. It's a complex algorithm, but for the purposes of this talk, this is what you need to know, that if there's some jitter in the network, BBR will maintain queuing delay that's equal to the propagation delay. And it doesn't matter what the nature of this jitter is. Now, if there are two flows for which the propagation delays are very different, they're going to maintain very different queuing delays. But they have just one queue. So the flow with the smaller propagation delay will interpret the higher queuing delay maintained by the other flow as congestion and slow down, and therefore starve. To validate this empirically, we have a two-flow scenario running real BBR kernel implementations emulated on Mahi on a 120 megabit per second link. One flow gets 40 milliseconds, and the other gets 80 milliseconds of propagation delay. And when we do this, the one with the 40 millisecond propagation delay gets just 8.3 megabits per second out of a total of 120 megabits per second, and this is more than a 10x difference. And as the bottleneck link rate increases, we prove that this ratio will grow arbitrarily large. Let's also look at the Vegas fast COPA family. Here, we again emulate a 120 megabit per second link and run COPA. And the propagation delay in this case for both flows is 60 milliseconds, except for one of the flows, we send just one packet at 59 milliseconds, just 1 millisecond lower. And this causes that flow to misestimate the minimum RTT, and therefore to overestimate the queuing delay, and get just, again, 8.8 megabits per second. And this is something that we discovered before we started on this work on understanding congestion control, and that's what motivated this work. So this happens in reality. Now, we've said that delay convergent CCAs cannot avoid starvation. So could deliberately varying and deliberately oscillating the delay help? We believe so. This is a conjecture, and this is the reason. So what ambiguity in estimating congestive delay does is that it discretizes it, because the CCA does not know what, as long as a delay measurement is within a bucket, it doesn't know where it is inside that bucket. And if the CCA is delay convergent, then it's basically going to be in the same bucket all the time, and the CCA receives the same bits of information all the time. And therefore, it only has finitely many bits of information, which it has to map to an infinitely large range of link rates. And that's a problem. So the reason we believe that deliberately oscillating the delay could help is that ambiguity is that now it gets different bits of information each time. For instance, it could encode the link rate in the frequency of the oscillation, and that can map to an infinitely large range of link rates. And we do show some evidence in the paper that this could work. So given this result, what do we do next? First is, of course, we could try to design algorithms that deliberately oscillate the queuing delay. We are not aware of any that exist, but we do believe that it exists. The second thing to do is that the entire problem came about because we tried to map a finite range of delays to an infinitely large range of link rates. So we could just stop doing that and design only for a finite link range. The techniques existing algorithms use do not map well to a large range, but we show a simple trick in the paper that we can do to make the range of link rates exponentially larger than existing schemes. And finally, we could just stop relying on congestion control to avoid fairness, and instead use in-network support, such as ECN or fair queuing. Thank you.
Questions?
So my name is Kees de Laat, University of Amsterdam. I have a question regarding the buffer. So in your entire talk, you said, well, large buffer, not so large buffer. Many of these protocols seem only to come into action when the buffers are filled. So the buffer times, or what is it, divided by link speed, gives you at least a certain delay that you always seem to include. So what does your talk tell to vendors what to do with buffer space or memory in the switches and the routers?
So as far as starvation is concerned, we believe very strongly that if the buffer size is small enough that the delay variation, the non-congestive delay variation is larger than the buffer size, then starvation cannot be avoided. This is not a proof yet, but we believe this is true. And also, the buffer size has to be larger than the non-congestive delay anyway, because in order to absorb the burst due to non-congestive delay. So I think that's the thing we need to keep in mind.
I'm actually not completely sure.
Can, like, let's say in your two flows competing case, right? And it assumes that each flow does all have some non-congestive jitters, delays. Would that sort of cancel out and make sort of this starvation problem less severe as in your sort of example shown?
So one would expect that the non-congestive delay for the two flows is different because they're on different paths. It could happen that they serendipitously cancel out. What we show is that there are some cases where it won't. And furthermore, we demonstrate that some of these cases are pretty common, likely to be pretty common on the internet, because all you need to break BBR, for instance, is just a slight difference in propagation delay and some jitter. And in our experiments, we didn't even need to add jitter explicitly. The jitter in the operating system and the emulator was enough to cause the effect.
Okay. I guess that's it. Cool, thank you.